Welcome to the last day of the Around the World conference. My name is Geoffrey Rockwell. I'm the director of the Cool Institute for Advanced Study, and I'm really pleased to be your host for this week of fascinating talks on different aspects of sustainable research. We at the University of Alberta respectfully acknowledge that we're situated on Treaty 6 territory, traditional lands of First Nations and Métis people. Today's topic is conscious computing, from energy consumption to the ethics of data visualization. Please feel free to ask questions. We've got a number of ways that you can ask questions. One way that you can ask questions is right on the streaming page. You can, if you scroll down, there's a box and you can enter a question and hit the button. Another way is you can tweet using our hashtag, hash ATW2018. Our website, in case you've forgotten, mind you, if you're hearing this, you know where it is, but it's aroundtheworld.ualberta.ca. And we really appreciate questions, and what we'll do is we've got people tracking them, and what we'll do is put them on a Post-it note and bring them to the chair. So without any further ado, I'd like to introduce today's chair, Ivan Fair, who is both professor and chair of electrical and computer engineering here at the University of Alberta. So over to you.
Thank you, Geoffrey. Yes, indeed. It is my pleasure to be here to chair today's first session, which is a panel session regarding energy consumption that's associated with our information technologies. We do have two experts who will be providing us their thoughts, Dr. Andrae and then Dr. Doug Barlage. And following that, we will have time for questions that you may have for our audience members. As we do so, we respectfully acknowledge that we are on Treaty 6 territory and that we have the opportunity to share our thoughts and wisdom from this venue. Our first speaker, Dr. Andrae, received his master's degree in chemical engineering and subsequently his PhD degree in electronics production, both from universities in Sweden, which is where he is today to join us. He's worked with Ericsson, and he's also been a postdoctoral fellow in Japan. Since 2008, he has been with Huawei Technologies in Sweden as a senior expert with life cycle analysis. Related to the topics of the forum today, Dr. Andrae's specialities include the application of sustainability assessment technologies for ICT solutions from cradle to grave, focusing mostly on resource efficiency, life cycle analysis, and eco-rating methods for mobile devices. So, with that, over to you, Dr. Andrae.
Okay, thanks. I try to share my screen now, and hopefully it works fine. Yeah, so it works. You see my screen? I hope.
Yes, we do. Yeah.
Yeah, good. So there's no problem with that. Yeah, the title of my presentation is, should we be concerned about the power consumption of ICT or not? Yeah, is the outline of the talk here, an introduction, the methodological approach and the data traffic trend, and then the emerging trends as far as electricity use of this production and the use phase of the consumer devices and the network infrastructure and of course the data centers. And then the synthesis of this global trend. Some short discussion and conclusions before the outlook. As we all know, there are conflicting messages regarding the path to power consumption under control. There is several different ways to measure this and estimate this. Different statistics tell different stories. And I think we got to prepare ourselves for truth about this power use we may not like or like. Incredibly enough, we might enter the yottabyte era in the next decade already. And if that happens, can the effect on the power consumption be understood from this sector? The ICT power footprint investigations themselves, you have some problems too limited system boundaries, some overestimation of power saving potential in the next decade. You assume that the historical power use, which has been low, can also predict the future global power use for this sector. With the key is this: the unprecedented data traffic growth is the little thing here. You assume that the Moore's law relation to digital circuitry can continue forever, and the problems with the power efficiency will occur for several decades, and no problems will occur for decades to come. Minor problem, the wrong slicing, some the different ways to set it up. But so the major question is: can this future infrastructure actually slow its overall electricity use until just a few years ahead, 25? Under which circumstances is the power consumption slowing down? What does it take for that? And under which circumstances is this power consumption rising? Look at the big picture here. 2015, around 22,000 terawatt hours was used globally. ICT is spread all across the other sectors. Here, just crudely said, industry, buildings, transport of goods, travel of people. Yeah, we can expect that transports of goods and people, you have electrification, so you will have more power there, but not so much. But it's not. It's spread across the different sectors, like 7%, something. Yeah, here's my scope of this sector, which is spread among others. You have the consumer home devices, clients, all of them, desktop, monitors, laptops, smartphones, etc., TVs, and some new ones also, AR, VR devices are coming. You have the wireless access networks, 4G, these kind of networks, radio, wireless networks. And then you have the fixed optical core wired access networks, broadband networks. And the Wi-Fi networks, they are like, mostly it's the modems at home, Wi-Fi modems at some networks. Then the data centers, including the cooling and the, not only the processing. And then production of all of it. That is usually neglected, but it's very important from the life cycle analysis perspective. For this kind of investigation, trends are much more important than exact use patterns and numbers, actually, as we don't know how and which devices will be used in the future. So you have to look at those things. But there are fundamental conflicts, for example, for wireless, between cost, bandwidth efficiency, and energy efficiency. So we balance there. And optimizing for energy efficiency will be essential going forward, different ways. Some major trends, Internet of Things, billions of devices, artificial intelligence, with pros and cons with that, augmented reality, virtual reality, crypto mining, fog, software-defined networks, virtualization, mobile age computing, which can increase the battery life of mobile phones. You have many ripple effects in different directions, very difficult. Technology development, high frequency, energy efficient antenna, gapways antennas, for example. This is not new, but you have seen a 35% annual increase of the average peak data rate from 2Gs to 5Gs, and the 6G, which is expected in 2030, will have 80 gigabytes per second. So 20 times higher rates for each G have been observed. So then you will have some global data trends. It's rising. I mean, the daily communication per user, humans, of course, then, but also there will be machines creating data. So I suspect that it can rise. That's my assumption, bearing assumption here, that it can rise quite quickly. Capita maybe is the wrong word here. What is capita? It's humans, but you have other sources which will generate also data. Now there are different assumptions how fast this rise will go, and how fast this will be emerge. But it's rising, and the share of the mobile communication, like no, when you have 5G phones and so on, then it will be more than fixed communication. So we'll do everything mobile, almost. Be able to do it anyway. Oh, and then some details about the blocks here. Production. Now, we are now at like 200 terawatt hours. You can get to that number by different techniques, LCA analysis of the different hardware. You know, it's and so we do this. These new devices, I assume, they will not increase the electricity use or production so much, but the smartphone share will increase its proportion of it, and that has been also confirmed by Canadian researchers from McMaster University lately. The share of the production of data center hardware and network hardware is expected to rise a little bit, but I have downplayed the importance of production because there are many techniques to have it under control. But as you see, the millions of produced consumer electronic devices will be like 28 billion just in a few years. Yeah. Then you have the use of these client devices. So there I had these slides are quite new then, understanding that it's dominated this use by processing and the displays. There are fantastic achievements here. So, I mean, for the years to come, and the downward trend is expected to continue. But we have this. It's the key issue here. I mean, the processing power saving problems related to Moore's law. If they happen around 22, as I imagine, then you can have a gradual upward trend. But there are many ways to allow improvements, as we know. I mean, so far I don't see that the smart home devices, wearable and AR, VR, their actual use phase consumption will not be a big problem in this. You still have the TVs and so on. Yeah. Right. Yeah, and then you have the fixed wired with broadband optical networks. Here also have a much more moderate estimations now compared to previous presentations and papers, because there are large energy saving improvements done, and you have the natural saving is still going on, but you will have some problems in 22 again. It will be more difficult. So everywhere you have processing, there will be difficulties to improve the power saving. The methodology is very simple, that you have for these networks and data centers, so that you have some starting values, confirmed or solid estimations from previous years, and then you scale up with the increase of the data traffic. But also the annual electricity intensity improvements have been huge. This is many other researchers confirm this. The question is, how long will they continue? Are there limits to this to these improvements, which are fantastic? So the base case scenario here is that it continues with no problem, and also the Wi-Fi is also, as people who are familiar with my work see, that this is much lower than previous estimations. So I take a little bit best case angle on this presentation. I mean, these ONTs, modems, gateways, they are improving their energy efficiency, but the numbers are growing. Somehow a little bit along the data traffic, but not correlated strongly. But the Wi-Fi backhaul infrastructure here is also expected to keep growing. You need more production of that and so on. But it is after 22, you will have a gradual decrease of the saving potentials for these small sizes. And then the wireless, which is studied in a little bit more detail. We have one scenario here. It is now at around 100 something, and as the 4Gs, of course, is very dominant. It's very energy efficient compared to the 3Gs. So we have a model where we have different shares, confirmed shares, global shares of different Gs. So we're saying wireless. And the 5G is it's like 10 times more energy efficient energy efficient communication than 4G. But there you have to be careful to swap, not use all of the Gs. I mean, the old inefficient must be swapped out. Otherwise, you will have higher consumption. And also, if the 5G is delayed for many reasons, you will also have extra, but not alarmingly high and so on. But and we have facts that these network operators, earlier years they have decreased their network power consumption, decreased actually in absolute numbers. So the improvement is very high, but there is uncertainty also. The data centers have somehow most interest, or should have the most interest, as they handle all the end traffic, the global IP data center traffic. All of the traffic has to be processed by the servers in the end, so they will have to take care of it. So this slide is completely new, and as you see, there is a best case scenario where the data centers, miraculously enough, could reduce their power consumption. But it's all unbelievable. But if the trend, if you have the data traffic doesn't grow as much as one can think in the base case, like 27% per year only, you can say, and this more than 20% annual electricity intensity improvement is continuing, then you will have nothing to care about. But if the data traffic takes off with new applications and so on, which is could be likely, and you will have some problems in like 22, a gradual decrease, to much worse improvements, then you will have a much higher. But maybe not as high as I have said before. But this is only, you can say, to 25, and also you see that 2010 to 2015, some operator they increased their power consumption. So there is some increase, but I can agree that now it is moderate. And then to synthesize this, you could have from like now 1700 to 1500 something, actually no problem in the base case, for these years. But you can also have an increase to quite much, like 3000. And this slide shows something about the renewable electricity production in comparison to this. You see this 3000 and 1700. In this 25, you see those bars there. There is also, of course, I believe that you have smart ICT, smart grids, smart energy savings, electricity use reduction. The latest estimation I saw of this is that it's a little bit less than previously understood. So, this graph shows the total global use and the ICT sector use for those two scenarios. So it's not a little bit higher than the IEA, but we understand where it will be. The renewable electricity is much higher in this case than the ICT will consume, but it's a theoretical match. So here is also not the 20 or so I was talking about before. When you look at this, it could be like now 7-8% to 10 or 5%. So it's not so much to be very much alarmed with in this kind of modeling it. And I agree with the criticism that the base case should be actually done in its full based assumptions, to see, not some mixture. So this is it. with and without this very considerable energy efficiency gains. This doesn't say so much. It's the improvements of the electricity intensities for different data traffic dependent technologies. And this is, I think it stands up, these figures, with the most positive researchers for this kilowatt hours per gigabyte. And this is two other graphs just showing what I've been showing before, but the proportions. And the new thing here is maybe that you have a higher share of the consumer devices than before, and not so much a move into the data centers. We have thought before that it's obvious that the consumer devices will be reduced dramatically, and that power consumption will somehow used by the data centers instead. But maybe that truth is not so obvious anymore. But the trend is the important thing. And here is some previous investigation also shows this, that then the more investigations we do with this methodological approach, the more we see that it's not as high as we thought 2012 when we looked at 2017. It's more less than that. But you can see for yourself what we thought in 2013 about 2017 and now in this presentation. Other countries, Japan here with a certain scope, is not data center, CPU production, and client devices are not included, so it's the telecom networks. But it's also, they believe in their research or prediction that it will rise under different circumstances. So most researchers think that we will have a rise. The question is how big it will be. So in summary here in the discussion, the speed of electricity intensity reduction versus the speed of data traffic increase. This is the fundamental dilemma or whatever. Higher variable outlook we will have. Variable at least, or highly variable, depending on starting values and percentile estimations of electricity intensity reduction and data traffic increase, obviously. But it should be finer resolution of both of these two major parameters, of course. If you have the rebound effects, the tertiary one, or the new consumption of goods and service and traveling. Traveling is a service now. So we know that this is happening. Is that then the ICT contributing to this behavior or the GDP growth? And then you have new consumption. So, there are ways to look at that also, but not that I want to share here. Just a remark about Hong Kong, which is a very efficient city, but still its annual electricity consumption is predicted to increase by 2030 for a year, to mention, because they also use a lot of technology and ICT, but still increasing. I say that to this question, it cannot slow its overall electricity use in the next 8 years. And for the first time here, I do this now. I take a really optimistic base case scenario presented, which takes into account this current improvement rate of the joules per bit in data centers and networks for another 10 years, and show that scenario. But this electricity power consumption for the present ICT scope I showed here in this scope, it will be very significant unless great efforts are put into the power saving features, and it's done. So it seems like planned power saving measures and also innovation will be able to keep the electricity consumption of ICT and the world under some control. We will see the answer in some years. I said it. The power use of the blockchain or mainly some cryptocurrencies mining could be another driver which cannot be ignored in the context of the ICT global power use. Artificial intelligence is very hot topic and research here. It's of course, most people say, yeah, it could help reduce the power consumption in ICT. We learn to do that. But it's also the goal of the optimization. But it can also foster more power. As, for example, I saw that certain 5G artificial intelligence optimization strives for unlimited data traffic handling. And as we argue here, the data traffic is maybe the main driver if you cannot control limits of nature. So then, we'll see about the artificial. But then the innovation and energy-saving technologies, quantum computing, light fidelity instead of Wi-Fi, underground data centers, perfect utilization in the data center should not be underrated. And then the intelligence shutdowns. How much can they give in this? We need them. So that's it. I hope I kept my time.
Thank you very much, Dr. Andrae. Thank you, Dr. Andrae, for sharing your thoughts with us regarding energy use in ICT systems, in particular in light of potential and expected continued growth in the data and the communications industries. It's now my pleasure to introduce you to my colleague here at the University of Alberta, Dr. Doug Barlage. Doug has been a professor of electronics, microelectronics, nanoelectronics for, he counts it to be 16 years. But I think that description is too narrow for his expertise. Prior to joining academia, he worked for Intel and was involved in their semiconductor design initiatives. Currently, although he is a professor here at the University of Alberta, he is on secondment to the U.S. Department of Energy, where he is responsible for a worldview, or at least North American view, of the semiconductor fabrication industry. In particular, its look at energy consumption and how that will play a key aspect in its continuing evolution. So he brings to this talk not just his academic expertise, but I think a larger worldview of the industry and just where it might be headed. With that, Dr. Barlage.
Well, thank you, Ivan. So I'll just give a little start by saying that for the last year I've been sponsored by Advanced Manufacturing Office at the Department of Energy. And really what we're trying to do is address the problem of the computation, or all this computation that Anders talked about, but we talk about this at the nanoscale. What can be done at the nanoscale to continue improvements so that you can continue to have lower energy per bit, and very similar to what Anders was talking about. And I think, when I was thinking about getting ready for this talk today, what we really look at is we want to do this in a general term and make this relatable about the energy that we use when we use the internet. When we use our cell phone, our computer, or one of the many things that interact with the larger cloud of data, we forget that we are exercising a certain amount of energy to do this. We just put that in the back of our mind. Unlike a light bulb, where the energy spent is at the point of use when we watch a viral cat video. And I think a lot of the conferences I go to, I hear a lot about the viral cat video that's going to destroy the universe, that this is going to somehow take down the internet because of the energy consumption. On our phone, we spend about whenever we do this on our phone, we're going to spend about 10 to 100 times more energy supporting the data path to get to it. And this is really what Anders has been talking about. For that matter, this conference on sustainability depends on the World Wide Web. And as we stream across the planet, there's lots of energy expended, albeit a lot smaller than the amount of energy that it would take to bring everyone to the same room at the same time. Now, this energy is what I want to talk to you about today and give you a little bit more of a conceptual framework to actually think about this problem on your own and actually relay this to other folks. And also to take a little peek into what the future is going to hold. I do think a lot of the data that we just saw in the last presentation really illustrated that very well. And I'll speak to that maybe in a less specific kind of way. And these are the kind of things that we'd like our internet to help and enrich our lives, but we also don't want to get consumed by it and by the energy that it actually takes. Okay, so we're on the next slide. And so, again, trying to get a simple framework with this, and you think about all the things that we use every day, all the different applications, and you think about all these things that actually take energy. And then when we interact with this cloud of applications, it takes a lot of background computation to move the data to where you want to see and to use it. Now, this is not free. It actually costs something. If your phone is using a joule of energy to do something, the computational system to get there takes 10 to 100 joules to actually get it there. So that's actually where most of the energy is expended. Now, this is an important idea. Now, if you think about that computational system as the elephant in the room that nobody really wants to talk about, it's this thing that when we are entering and using the World Wide Web, everyone takes for granted. It's there, everyone takes it for granted. This computation takes a lot of effort and energy to bring that content to the user. Now, while the modern computational system is obviously a little bit more complicated than the abacus that comes from sometime around 3500 BC, the principle is about the same. A user tells the computational system what it wants, and the computational system does what it takes to provide the user what it desires. Every time the computational system moves a beat on the abacus, the computational system takes energy. In engineering terms, you can calculate that energy fairly precisely. And for reference, my phone, fairly simple device by current standards, has about 1 billion abacuses inside. Okay, so when the calculation system does its work, it takes energy. Some of the energy is used to move the beads on the abacus. And the other energy is required just to maintain the computer. So you have to supply both things to make the whole thing work. You have to keep the computer alive by feeding it, and you also have to give it enough food to actually do what it wants you to do. So just as if we had 1 million elephants, we'd have to feed those elephants to keep them well, and to have to feed them also takes energy to actually do the little bit of work. So, and if we go back, maybe a little bit more tangible thing to look at is actually you look at some of really what we're looking at here is one of the first computer. This is a Babbage machine from sometime in the 1800s. And in there you actually had a lot of little switches that were used to throw things back and forth. Modern computational apparatus and architecture today, we'd like to think we're a lot smarter than we were then, but it's really just a direct descendant of what you see in front of us. It's just that there are a lot more of them working in a lot more ways together. Now, what's nice about this from a demonstration point of view is that you can see what's going on inside. You can see this with your eyes rather than relying on electron microscopes to get at the mechanisms of how this works. Now, the principles of operation will state that if we move a switch from on to off and vice versa, we will require some energy to make that switch from on to off. So every time that we change a state inside that machine, it requires a certain amount of energy. This energy required, at least for the case of that simple machine, can be calculated using simple Newtonian rules that are part of the first lecture in the first year physics course. Now, energy is equal to the force applied required integrated from the position from the on-off state, and we can reduce energy by making the mass smaller and by reducing the force. Now, reducing the distance between the two states, making these things closer together, is an objective to make the thing work for less energy. We can also reduce the force required to move the object, i.e. you can actually oil the machine. So essentially, these engineering objectives are still in play. You make things lighter, smaller, and less resistance, and you'll make your machine more efficient, so it'll work more efficiently. That is the engineering principle that drives a lot of the positive developments that have allowed us to get the vast amounts of data that we're using today in an energy-efficient manner. Now I'll talk just a little bit more about that. So, and then you look back to the first computer. Back in 1946, we had the ENIAC from the University of Pennsylvania. In this case, it's reported that the energy required for this system was about 150 kilowatts. And this total computer system fit into a small room. Now, for reference, what is 150 kilowatts? What does that mean? 150 kilowatts is about the same amount that a modern electric vehicle expends when it's accelerating to a cruising speed. So this is something that is completely manageable by today's standards. We could build ENIACs, okay? They're not too energy consumption oriented, but in 1946, when the real loads on the electric power grid were light bulbs and heaters, this was a significant amount of energy. And if you look at this, for an individual operation, it took 100 joules to do one operation on this old system. It's hard to make a comparison to what that energy actually means. But I'll give you a good example here in terms of something that we can relate to and is actually interchangeable in the human condition. If you look at about a peanut has 11 calories, okay? There are 4,184 joules in a calorie, and if you perfectly convert that peanut, that's going to give you about 460 operations for one single peanut. So ENIAC may have ever so slightly more efficient computing power than the people who are actually operating it. But ENIAC was faster than the people operating it, and it could execute around 300 multiplications operations per second, so that ability made it useful. So to keep ENIAC on, it required 150 kilowatts. Of that 150 kilowatts, about 30 kilowatts was used for calculation. So when Anders was talking in the last presentation, when he was talking about those advancements, it was really about keeping the system operating for lower amounts of energy. That was the primary thing that was actually really being looked at, and that's where the advances were being made. And at this point, while a large energy consumer by 1946 standards, it didn't necessarily make a dent in the overall worldwide energy consumption. Now, things did manage to get more efficient as time went on. If looking in the vacuum area, which is ENIAC, starting with ENIAC and moving through 1960s and forward, you saw that the demand of the supply of the computer systems ended up driving the power density down. And if we look and start in 1980, okay, well, before we get to 80, we're going to talk a little bit about 1960. Hewlett-Packard noticed that solid-state components would comprise 90% of electronics and computing infrastructure in 1970. The big advantage with solid-state components over traditional components is that you can move them closer together. Moving them closer together made them more energy efficient. It's really that simple. And at the time, less than 10% was solid state in origin, but they recognized the potential to move elements in closer, and they were smart enough to recognize that the market force was going to push things in that direction. Now, around 1965, and as we heard in the last talk, we'd heard about Moore's Law, but in 65, Gordon Moore was just a brash young engineer who made a bold prediction that things got more dense by a factor of 2 every 2 years, and that it would continue to do so for a long time, and with respect to logic. What he did not consider at this time, but was also true, was that the energy was also in a steady decline by about a factor of 2 per operation every 2 years. That didn't figure into his calculation. The only thing he was worried about was putting more components closer together, because that made the cost of things go down quite a bit. Since about 1980, energy consumption began calculated very easily with some very simple calculations. And here you can see, moving from the IBM PC that entered the scene in around 1980, down to today, where you have like a Snapdragon microprocessor, which, believe it or not, has the most advanced technology on the planet. Your cell phones are actually the leading edge of technology. They're not the behind anymore. The most advanced technology is found there, not in big server farms or big supercomputers. And during that era, what I just described, from 1980 to 2015, this is roughly regarded as the Dennard scaling era, but now we're at some other kind of crossroads. And what that means here is that even though that things continue to move down, did we actually reduce the amount of energy used worldwide? And the answer is really no. And what happened in around 2000, I think 2000 is a good year to pick for when things really changed, when manufacturers of equipment, manufacturers of information technology, things changed. And if we look in 2000, worldwide energy consumption for computation was just a minor consideration for overall energy consumption in the world. Refrigerators were a far bigger concern than computers in the year 2000. And they still are a pretty big concern. But 2000 is a good year to choose as a time when we transition from using discrete computers as our primary resource for computation to when we use network resources as our primary values. Now, Metcalfe's law, Metcalfe was an engineer working around 1970 who worked on early internet ideas, but what he did was he recognized that the more similar devices that are connected on a common network, the greater value of the collected network is by a factor of n squared. Now, when this happened, value increased dramatically. The example is Google. Google has gone up at least 20 times since its inception, since it was its first IPO. The number of users squared indicated the amount that it actually grew. It's even better, that numbers are even better for Facebook and Amazon. More users mean more value, so we create more machines and more computation. So more machines were attached to the internet, and the value of the server farm was starting to be recognized by business, universities, and worldwide, and that's actually what gives us to the state today. If you look at the chart here, we actually see that in 2% in 2003. So that quickly, from 2000, when it wasn't a blip on the radar, to 2% in 2003 by the introduction of more and more connections. That's the power of the internet. And 6% is in 2012, and as Anders relayed in the last talk, it's somewhere closer to 7 to 12% today, depending on how you do the calculation. And what happens, the irony of actually making things more efficient is something known as Jevons paradox, and it says that as you make a resource more efficient, or it can extract a resource more efficiently, society as a whole will not use less of the resource, it will actually use more. So when things get more efficient, more people want those things. We lived in a world where advanced computation was only in the domain of the businesses, the government, and the scientists who needed advanced computation. That's prior to 2000. Today, everybody uses advanced computation, whether you believe it or not. Next time you watch a Netflix movie, you watch a YouTube video, you are experience the product of advanced computation. Now, so the number of operations during this time has increased at an extremely high rate. Now, the energy of operation has in the past decreased at almost an equally fast rate through around 2015. The combination of these factors is what drives the demand side for computation. So the underlying switches of consumer technology, cell phones and Xboxes, and the technology that you find in the server or the supercomputer are essentially the same. So what you have inside your cell phone is the same thing, except there's a whole lot more of them inside of a server farm or inside of a supercomputer. And the difference is just the scaling of the size. But there's still the same inside of here. And if you look at some of the recent results here, if you look at some of the top 10 performing supercomputers in the world, you'll see that in the fastest computer is capable of 90,000 tera operations per second, or 90 times 10 to the 15th. That's not a number that we can really think about very well. So I had a chance to visit Titan, which is the U.S.'s largest supercomputer last year when I was in Oak Ridge, Tennessee. What you have to realize when you walk into a supercomputer facility is that you're walking into a room that's filled with rack after rack of computers. The size of the building that is housed in it is about 10 times the area of the computers. This partially supports the people that use this computer, but more importantly, it houses the air conditioners and power management systems that are used to keep the thing operational. The total energy consumed at Titan is around 8.3 megawatts. So remember, ENIAC was about 1.5 kilowatt. You can do the math to see how much things have gotten more energy intensive to do computation. Even though the amount of energy per operation has decreased by about 1 time, that's a big number. I don't even want to say it. It's a big number. So if you go 200 kilometers or so to the east of Titan, and this is in North Carolina, you're going to find one of Facebook's server farms. And there's a picture of it that you see. And it's located near a hydroelectric plant, and the total energy consumption is actually not reported. They actually don't advertise, they keep that fairly confidential. You'd probably find it if you wanted to look hard enough, but they keep that fairly confidential. There are no people there, and as most of the users are actually remote. Most of the users are sitting back in the bay, enjoying the view of this Golden Gate Bridge or whatever they're doing at Facebook headquarters. But if you just do a scaling of the size based on what you see at Titan, so which is more, Titan or Facebook server farm? By a good estimate, the Facebook server farm is probably around 10 times more energy, 10 times bigger use than the supercomputer which is essentially the fastest supercomputer in North America. So what happens when we can no longer increase efficiency with smaller bits? So Moore's law has been very good to us up till about 2015 or so, and then it has actually managed to increase efficiency by decreasing size for the last several decades. And if you see what you look here and you see where we're at, this is a slide that I actually, the picture, it's a version of a slide that I generated back in 2000 where you see a piece of DNA that's equivalent to what a transistor looks like now that was a research transistor back in 2000 when we generated those devices, but it's a production device today. So that's actually, the DNA is about the same size as the piece of transistor. We're going to have a hard time making things much smaller than that. Today, that's what's in production, close to it, and you see a slight snapshot over it when we look at the Intel picture over there, where they report what they're actually producing every year for a given size. And you take a look at it. Now, what's happened is that the transistor density per area, the transistor density is steadily increasing, but the absolute size of it is not necessarily increasing. They're able to push them closer together, but they're not able to make them smaller themselves. So they're not able to reduce the energy that significantly. So there's a reduction in the ability, based on physics, that you can no longer actually achieve increased efficiency just based on physics. Up until 2015, Moore's law gave everybody in the system design basically a free break because it made things more efficient with respect to time. Now on slide 9, here we have we take a look at the worldwide energy consumption and the worldwide energy consumption just due to the computing. And if you look at today, well, you look at all the lines at the top, this is where energy comes from, okay? And you take a look at there, and what it's projected to be up through 2040. And I think 2040 is chosen is because if you're going to build a nuclear power plant, you have to start planning today so that it's online in 2040. So this is what the U.S. Department of Energy does, amongst other things. And then they actually, you take a look at it and you put a sticker on there and you say today 7 to 10% of the world's energy supply is consumed just to support computation. Okay, all the things that we use, 7 to 10%. Again, 2000, it wasn't on the radar. Today, 7 to 10%. At steady rates, you see this is going to keep increasing. Now, if I look at what I showed there, that difference between the red line and what we're actually using, that's just the amount of energy to keep the computation system alive and healthy. The red line is just really the demand for the amount of bits that you're actually wanting to use. So there's a difference between the yellow line and the red line, meaning that or the yellow dot and the red line is what we're actually getting, and the yellow line is what we, overall what it takes to actually keep the infrastructure alive to do that. And if you take a look at this further, we have some engineering solutions to get us closer to that target line to make things more efficient. So we might be able to keep at that 7 to 10% level for the next number of years. But even at that rate, our demand for data, the worldwide demand for data, would overtake the worldwide capacity to to generate power to support it in 2040. Okay, so we have a lot of engineering work here to actually worry about. And then if you look again, there's a theoretical minimum over there, and that's what we'd all like to do, is actually figure out how to get to that theoretical minimum about what to do with information when we can get our information and computation basically for free. So what's next for demand? What keeps driving us? As was said earlier, emerging demand is that you have self-driving cars. That is going to take a lot of data. That is going to take an enormous amount of data, an enormous amount of computation. Virtual reality. My kids are really excited about that, and I'm not so sure I am. But this is going to take us, the amount of data that you're going to have to transfer from one place to another gets to be even more mind-boggling. You think about the Google Glass, what that will do is going to do even more. So artificial intelligence and cryptocurrency are also things that are going to drive up that demand. And to get those solutions, we want to move to that ideal limit. And the other thing is actually we want to have some kind of more efficient computing. Neural networks seems to be the near-term idea, and this is really inspired by this idea that a human can take on the world's fastest supercomputer and win, sometimes, okay? But the difference is the human works on a hearty breakfast, and the world's fastest supercomputer takes enough energy to power 20,000 houses for a day. So you can decide who's the real winner there, even if the human loses by a close margin. So if you look at why it's so difficult to make advances today, we're down to only 4 places in the world that can actually do research at this nano scale, or do things at the nano scale that are meaningful. And it started off back in 2000, it started off as 25 different places, and now people have been driven out of the business, so it's down to just 4. And the reason they're driven out is TSMC, which is actually one of the world's largest producers of chips, announced that it's going to take $15 billion to actually build a new plant, and that's going to be online around 2022, I think, is what they actually said. So the problems here that we have, there's really no new device technology on the horizon that's going to provide an immediate solution. We no longer have the benefit of Moore's law to help us make energy come down. And the other thing that's actually a problem, and especially when we think about the implications here, is that as data becomes more scarce, a more scarce resource, it's going to become more valuable, and you create a danger of a new kind of inequality almost. Access to data and not access to data. So what's going to happen? World's demand for data is not going to slow down. Server farms are going to continue their efficiency improvements, and that's a good news. That means that we're going to maybe take all the way out to 2040 before we have a real problem. And some of the things that are also going to be done is software is going to provide some intermediate relief. The software designers of today have had a luxury. They haven't had to worry about this. But as we go in further, this is going to be a new parameter that the software designers are going to have to worry about to make their machines do the same task with less power available to them. But I think the biggest, scariest thing from my perspective is there isn't a technology solution there. We've had a technology solution. Right now, there is not one. And so it'll be an interesting few years as we get that all figured out. So thank you.
Thank you very much. Thank you very much. We have a few moments for the discussion. And if I could, Anders, I'd like to ask you, on your final concluding remarks, your statement was, well, you think that we can keep things under control in terms of data or power usage for computations. I didn't get quite that sense of optimism from Doug, who's saying, we're not sure where this is going. I just wonder, Anders, if you have some remarks about about Doug's view looking forward?
Yes, many comments probably, but yeah, this with nuclear power plant planning is something also, but that's a different rock. But yeah, I agree with Doug. I mean that the problems are sooner than we think. I mean, for this, yeah, I mean, I've been criticized so much for making too bad like some projections about almost that it will spiral out of control much earlier. But it's so difficult to make these predictions because now we don't, as Doug say, also see the problems so much. So okay, it could continue. We will find a solution. Yeah, but I mean, I think that, I mean, yeah, I mean, it would be very. I don't hear so many talk about this. Also, I mean, in the press and so on, that this ICT sector have this problem. So maybe it's just a few academics talking about it. So then I'm also start to get, that people are not. This is not really a concern. But I mean, the data will grow, and that's what I think will drive the power consumption up. Yeah. That's the only thing I'm totally certain of, that the data traffic will grow exponentially for many years to come. And then we can all have an argue, can we meet this with power saving technologies in other ways? But I mean, Dag is just another researcher who say that we have some problems. You know, some say we don't have problems. You know, but I agree with Dag that maybe I'm more moderate than he's. But
I just like to respond. I think we actually agree pretty closely up to about 2025. I think it's actually just that when you keep going on the same trajectory, we get some problems. And I think what you're saying is that there are some nice engineering solutions that's going to enable us to keep things at bay, keep that power demand at bay to provide more bits. I agree with you. But I also, there's the other issue that continuing past that point, there's the number of solutions becomes fewer and fewer, and so it's the near term. I think we're really close to each other. I think with most of the data that you projected and the data that I projected, so not too far off. But it's that when you don't, what happens after that is actually there's not a magic bullet that we had and we got spoiled by. For 35 years, which was Moore's Law. Moore's Law is the magic bullet that is gone.
So there's a question.
Yeah, some say it's not gone. It's not gone. Some people say no, it's still going on, and we will. But more and more serious researchers say it's a lot. But yeah, it's. But will we hit a brick wall? And nobody pretends that this elephant in the room doesn't exist. We will just 22 hit the brick wall. No one really believes that. Or we'll have inequality, internet, or it will be regulation of data, the growth. You know, but who believes that really? You know that you will have. You know, but do you think, Dag, that we will hit a brick wall in this sense?
I do think that there will be, one of the things that if you look at what Google spends on every month, they have payroll. Okay, that's their number one expense. Their second expense is their power bill. So they have a motivation to actually solve a lot of these problems. So a lot of those lower, easier access solutions, they're going to get to. And they're probably going to end up sharing that, or at least through one means or another, they'll pass that on to other people with servers. And so that I guess demand, because it's so expensive right now, just to have these server farms, it's going to drive the cost down to some kind of a reason, or the energy cost down to some kind of a reasonable level. So I think, that's the one thing that we got going for us, and Huawei is going to be a big part of that solution, as well as Cisco and other people that supply, the backbone of these devices. but it's
Yeah, I mean, the utilization is, some say this is one that it's so low utilization in the data center. It's an easy pick to have everyone should be like Google's PUE 1. If all data centers, the distributed and the centralized, are as the most efficient Facebook and Google data centers, then maybe that is the solution in the near term, to regulate that you have to have a high. But it's the law of economics and so on. You cannot, companies, they have to take some measure to what they cannot not know what the data traffic will be, the demand. They don't know it. Okay, but it's exciting to see. We will get the answer in just a few years. We will see, what will happen, with everything.
Thank you.
That's what it is.
Thank you,
Okay.
Andrae. Dr. Andrae, thank you, Dr. Barlage, for your very informative and interesting talks, and then that discussion that we were able to eavesdrop on. It's interesting to hear world experts share their views on this. Thank you to all those who have joined us for this panel. This discussion must draw to a close, but you'll be right up with the next one coming up. Thank you very much.
Thank you. Bye-bye. Bye-bye.
Okay, I'll stop that. Hello, and well, I'd like to thank our previous panelists and the chair, Ivan Fair. And now our next panel is a roundtable on minimal computing, and this will be chaired by Roopika Risam from Salem State University, and will include Alex Gill from Columbia and John Simpson here in Edmonton from Compute Canada's Digital Humanities Specialist. So over to all of you.
Great, good afternoon. Geoffrey just stole what I was going to say. So let me go ahead and get started. So Alex and John, the theme for this year's Around the World Conference is sustainable research. So perhaps you can tell everybody a little bit about what you envision minimal computing as, particularly as a discourse and practice of sustainability.
I'll let you start, Alex. Go for it.
All right. I think first, I think it's important for some of our audiences that may not be familiar with the term minimal computing. Really quick, to Google Global Outlook Digital Humanities Minimal Computing, you'll find there some resources, some thought pieces that more or less outline. In particular, I recommend Jen Sayers a few definitions. Right here live, real quick, minimal computing is the reduction of complexity and cost in the use of both hardware and software in order to try to maximize the benefits to all of us. And benefits here understood as a range of things, including sustainability, but not limited to it. Care for the environment, bandwidth cost, the reduction in the price that underpaid labor pays for the production of digital projects, et cetera, et cetera. So focusing just on sustainability, I think minimal computing makes it's an important gambit as we try to play futurist in terms of what may last and what may not last. By reducing complexity, I think we have a better chance of producing forms of knowledge that can outlast us without causing too much labor problems down the lines for those who will inherit them. That's very briefly what I believe, and we can discuss it. Now, John?
Yeah, absolutely. I agree with all Alex's things, and I had the privilege of being part of the Global Outlook DH initiative when it started, and involved with the minimal computing piece. And I now work for a group called Compute Canada, which does a lot of high performance computing, supercomputing pieces, and so it might seem to be the other end of the spectrum there in terms of, we might think minimal computing, very small computers, Raspberry Pis, things like that, versus cluster farms that have tens of thousands of cores in them. But I think there's a strong relationship there, and I think the last panel said it really nicely. We're looking at a future where right now 7 to 10% of the world's power is consumed in computation, whereas 18 years ago in 2000 it wasn't on the radar at all. It wasn't even something that was being tracked, and I think they summarized it nicely when they said in some ways that the internet is to blame for this, as it's raised our need for data and sharing, and we now not all of us, it's not fair to say that for the world, but many of us carry multiple computers around on us all the time, or we rely on them in this way. And so when we think about this potential for excess, on the other side, making sure that we're doing it smartly, in a way that's efficient, and as Alex had just said, in a way that doesn't put a burden on future generations unduly.
So if I could push a little on this point about reducing complexity. I mean, I've had the privilege of seeing Alex. Actually, Alex taught me how to use Jekyll, for example. And I've seen, he's done these workshops, a lot of people, and there's often a lot of anxiety around, getting into the command line. And we're sort of simultaneously saying this is reducing complexity, but for people who are more used to working in content management systems and kind of working directly in the back end, they don't necessarily see this as reducing complexity. Is there a way that we can think about framing that question of the reduction of complexity for people who, for example, might have anxiety around going beyond the graphical user interface?
Or the modern laptops instead of a Raspberry Pi. So yes, I always try to be careful, and I'll go back to the recording to see if I actually said it this way. But when defining minimal computing, to use the word overall complexity rather than complexity. For me, I tend to think about both our use of technology for projects specifically. In the digital humanities is a sort of aggregate of several constituencies and their work, and several technologies and the work they do in the machine. So if I reduce complexity in the overall system, perhaps sometimes that complexity will be increased for the scholars who are not that familiar with this new, with the terminal. They're not new with the terminal, or plain text editors. So there is that sort of bind that in order to reduce the overall complexity of systems, sometimes you have to push one of the constituencies in a direction that might be uncomfortable for them and that might imply more complexity for them. In the end, though, this is also trying to counteract some of the tendencies in technologies that are probably born with the way that Mac thought about the use of metaphors in order to design their desktop systems back in the early 80s, as Dennis Tennant has argued in his book Plain Text, in which this emphasis was on reducing the complexity of the users in order to make computers popular, led to sort of the technology that we're the most familiar with today. And in that sense, perhaps in digital humanities and in scholarship at large, we have not really divorced ourselves from this world of metaphors that privilege the user, the consumer. Even in content management systems, we may believe ourselves to be producers, but there's usually layers of other types of producers that sustain that, maintain that layer. And this thinking about them, in which I don't mind increase the sort of difficulty for people who have to transcend the metaphorical layer.
Yeah, and I really, Alex and I agree on so much. So the piece for me with the complexity is that sometimes we use the word complexity, and what we really mean is something that we're just not familiar with. It's difficult to say that a text file, when you open it and you see that it's really, for the most part, just the words and the punctuation is more complex than a Word document. So if you try to open a Word document, not in Word, but in a program that reveals its nature behind the scenes, there's an extent of complexity there that is quite difficult, and it's filtered through us through the programs that Microsoft and Google Docs and so on and so forth produce for us. And with that, there's a cost to it, and that is, well, I can't share this file around in ways that I would like to. And as helpful as they are in terms of providing export features and so on and so forth, that's additional work that needs to be done there. And why is that there? Well, it's so that it's easier for us to consume. But it's only easier for us to consume in certain privileged states where we have those systems, perhaps we paid the licensing fees, and that we really want to use it in the way that they're imagining that we would. When I work with researchers, they often come to us, and this is true for anybody in these support communities, because they want to do something that's a little bit more. They want access to the raw, real data. And when it's wrapped up in these complex environments, it gets in the way. And so if we start from the least complex, if we start from something like a text file, in many cases, it's not always the case, and there's media cases that are different, but if we think of text as a basic and we build from that using certain tools that allow us to add the complexity in layers as it's really required, as opposed to starting from the highest complex layer, things can be better for us in terms of removing some of that privilege that those of us who have access to those systems and those licenses have. It does, in some cases, mean moving beyond a graphic user interface, and that's going to challenge people's comfort levels. But in some cases, it might just be using a graphic user interface in an informed or maybe a smarter way, one that thinks about the things that are in the background.
I mean, I think what you just said, John, does a good job of demonstrating some of the ways that minimal computing aims to be a more sustainable kind of practice than perhaps sort of the, I guess we could call, I don't know what we're calling the opposite of computing. There we go. So I'm curious to hear you both talk about sort of how you see the term sustainability being useful currency here. Does it really capture the core values and methods of minimal computing, or should we be looking for alternative ways of speaking about it? So, Alex, for example, you've used the term durability instead of sustainability on your minimal edition Jekyll theme. Called Ed, and Gentry Sayers, who wasn't able to be with us today, he suggested that the term negotiated endurance, following Daniela Rausner and Morgan Ames, might be a useful one. So if you could say a little bit about whether you think we're even using the right terminology here.
So Gentry and I have been having this conversation for the past few weeks after we received the invitation to participate in the global, in this event. And I think both of us have problems with the word sustainability because of the way it's being used. It's not necessarily that there's something built into the word that prohibits us from using it in the future again. But right now, part of the problem is that sustainability came into prominence in the current systems of production and the ways that collaborations have been set in the academy today with scholars on one side and what are called service providers on the other side. And sustainability, as it has been used, sort of has implied that there will always be service providers in the back end that we don't have to worry about that will sustain these things. It's also it's kind of part of this process of the forgetting of the maintainers, who are the core of most of what we do. So an argument that many have made already, that we have to pay more attention to maintenance than to creation or innovation or disruption, etc. So in that sense, I prefer to use durability just for my purposes, Ed, there in terms of the way that these objects created with that tool, with that stack that I made, can live independently of us as flat files. Nobody has to be there to maintain a system that will generate them constantly. So in that sense, they will have more durability without making that implication that somebody will sustain it. At the end of the day, it is usually the culture that decides what lives and what survives. It is each passing generation decides what are the things worth saving about the past and what are the things worth passing on or repeating or redoing. And in that sense, minimal computing perhaps moves away from sustainability and towards, I like this negotiated endurance, towards a negotiated endurance in which, communities of laborers, hopefully working under more equitable conditions, decide what these things are without us having to put too much of burden on them to make those decisions. John?
Yeah, and again, sustainability has some value, and its value is really the term sustainability has some value, and its value is kind of an entry into this discussion. But as you begin to dig deeper, you discover it's really kind of carves off just one piece of that. And Alex has pointed to some human pieces, right? When we think about sustainability, we're usually thinking about power and material objects, right? So where are the minerals coming from that produce the computer systems that we enjoy and consider to be a necessity today, as opposed to maybe the human conditions that the people who are producing those things come from, right? And sustainability, in one sense, kind of hides that and some human rights issues that are there, either in the sourcing of those materials, in the production of the code, as well as the durability pieces that they're there as well. So I do like negotiated endurance, I do like durability, I do like sustainability, but there's not that one term that really grabs it all for me in this whole kind of package. I like minimal computing as a concept because it opens the door to this discussion, which we need. But again, it also, unless you're having that discussion, you don't see all the facets that are there that need to be brought out. So I'm still looking for a term that kind of grabs that package for me. Not so much for me, but for anybody that I might have the conversation with.
And I would add also that I think maintenance is really misunderstood. I was having a conversation the other day in which somebody said to me, well, we're done with the startup phase. Now we've moved into the maintenance. We need less support. And I said, actually, no, we don't need less support. If we need less support, it's assuming that maintenance is this sort of very static thing. And instead, the maintenance phase of any project can actually be very iterative as well and still require labor.
Absolutely, because software never needs to be upgraded, right? Like that never happens. Well, this happens all the time, right? And so when grants come off, and from the research perspective, when grants come off of that development phase and they go into maintenance phase, this can be debilitating for projects, right? Because they lose their development team, even though their platforms might have been stable, a shifting software architecture, a shifting hardware architecture, particularly when, these things are built to become obsolete, right? In some sense, right? Like we desire new ones, right? Whatever stance you take on Apple's battery kerfuffle, I think this is representative of how these systems work. And here in the research areas at the universities, we get a system and it's planned to be there for 5 years, right? And then where do those other pieces go? How much thought is put into how will they be used in the future? Do they just get shredded up and attempt to be recycled? Could they be used better in a smarter way?
This is something that I like to think of in terms of temporalities that go back and forth decades. So looking ahead at perhaps what we may leave behind, but also looking back at the 70s and the 80s to see what was there that is still really good. So in a lot of the ways that we've gone about designing these projects here under the rubric of minimal computing, focusing on the software side of the house, and that's Ed, Wags, in the same boats, and the way we did the Essex Archipelagos project is at least 3 of those projects have been built around the sort of static site generation and the creation of flat files that use plain text as their end result, and they can actually be served on the internet through storage. They don't need a LAMP server, for example. They in thinking about temporality in these things, we have used some of these old technologies, Unix, plain text, HTML has a good run so far, etc. Avoiding the use of contemporary systems that have to dynamically generate these files so that we have to keep the software alive. And that also come with security flaws, right? As we all know, the Panama Papers happened because of a carousel plugin on WordPress that sometimes people in digital humanities use. Now, the other issue about temporality that we always keep in mind when we do this back and forth is also we have tended to prefer the temporalities of the 70s and the 80s in terms of publication to the sort of continuous eternal present of the spotless mind of these kind of continuously content generation of today. So our journal, for example, runs in the old model of like one issue per year, and we also put caps on the duration of a certain project, saying, well, at this point we'll stop the data entry, and we don't continuously publish. We actually have dates on which we publish or release these things, and don't add things the next day or in that same week. In this sense, I think these two strategies related to temporality can be useful here in terms of thinking about maintenance because they do make it easier. So, for example, it will be way easier for people in the future to maintain these flat files that we're generating as long as the storage systems work. And as long as browsers can read HTML, these documents should exist. And as long as our machines are capable of reading plain text, which I think is a very solid gambit, I think we should be fine without increasing the cost of maintenance. On the contrary, reducing it.
If we could go back to something John was gesturing at a little bit earlier, we are sort of stuck with the fact that even the most minimal of computing practices are relying on exploited labor, land, and the health and the welfare of people, particularly those in the global south. So, for example, we could think about the suicide nets on Apple buildings in China, or e-waste, right, getting dumped in countries in Africa and Asia. So my question is, how can we, or can we even envision minimal computing as an ethical intervention in those issues?
John?
Yeah, and at some point, at some point we should, right? Particularly if we're going to talk about it in a research environment, right? Where we're talking about it today in academic environments. This is something that should be part of our discussions in terms of how we do our work, particularly when more and more disciplines are turning to computation to solve some problems. They're asking new questions, and with those questions, very thoughtful people, they should be asking as well, where's this research, what's really enabling this research? And as much as we might talk about the computation layer as kind of being transparent and easy for them and so on and so forth, it shouldn't come without question. So I think academics and universities have a really strong place to play here in terms of asking questions of an ethical sort. So if you're going to do research, you have to do that research ethically, right? You typically have to take certain pieces to an ethics board. Maybe how much computation needs to happen in terms of your power that's going to be consumed. Where's that hardware coming from? Was it sourced appropriately? If I'm going to do, I can't think of a non-bizarre example, but for traditional research, if that required, I don't know, if we're going to do research with cars or something like that, and those cars were sourced through child labor, and that was found out, probably we'd find a different way to do that research. Just because computers are a little bit more ubiquitous and seem to be necessary or transparent in some way doesn't mean that we shouldn't be similarly asking those questions. And there are better and worse sources, and we should be working as academics to question those and ask those ethical questions. So I guess the too long summary of that is maybe some of our computational use and practices should be subject to some ethical consideration at academic level.
Yeah, I agree, and I think perhaps the academy has a role to play here on two sides. both sides require massive collaboration. On one is to pressure industry to actually figure out better ways to sell machines at a consumer level that actually take into consideration these ethical questions, so that the actual minerals don't come from child labor. So the academy can perhaps put some pressure on them through political channels. And of course, we teach our students to think about these things. Perhaps they, as citizens, will also be able to put pressure on these companies to do so. There are other sectors of society, of course, that have to join us in this, because, as John pointed out, these are thought to be transparent mostly because they're ubiquitous. And the reasons we use them is because they are ubiquitous. So in that sense, at least while capitalism is alive, this is one of the practical possibilities that we have. The other one is through our own research. So in this coming more from science, natural science departments, looking at ways to substitute some of these minerals, or different ways of doing the circuits, doing the boards, etc., that perhaps can obviate the need for these minerals that are exploited this particular way. But the minimal computing, the small contingencies of us who are starting to be interested in these practices of minimal computing tied to DIY, we can also play a smaller role too in tinkering and figuring out ways how to create mechanisms that actually can minimize or eliminate the need for this forms of exploitation.
Yeah, I think that the challenge is that we ask ethical questions and we don't have the answers, and then sometimes stop it feeling good about having asked the ethical questions. And that's really that's kind of not where we need to be stopping. Something maybe to also add to that is thinking about collaboration, or what can be given back to the communities that are affected by these forms of exploitation. So I think, for example, about Juan Stein in South Africa and his colleagues are doing work with Raspberry Pi. Alex and I were going back and forth about this. That is, of course, based on the same. It doesn't get away from these ethical problems around sourcing materials, but they're using those to create Wi-Fi hubs in under-resourced and in many ways forgotten communities in South Africa, and so that's potentially another direction. And I think you might have done some of this work in Cuba, right? Working with DH on a stick.
Yeah, and John, you want to say something?
Yeah, so we had the privilege of having a conference with the Implementing New Knowledge Environments group in Canada. They held it in Cuba, and we got to meet some of our colleagues. And it was really interesting to see the practices that they had put in place to make research possible for them. And so one of the things that was just a practice was they would have these USB drives, and that would have the software that they needed, perhaps an operating system, the research data, because they didn't have the network infrastructure to pass these things around. And so there were these formally informal social networks where this information would be passed around. And so a very practical piece for them. And for us, we wanted to help that, and so we wanted to get them more USB drives and so on. But it was also a theoretical piece, like what's truly essential for me as a researcher, as an academic, or as just somebody using computers. What do I really need? We have these laptops, right? And they're all fancy and expensive, and they're super powerful, but when you strip it right down to the end, what's really the essence of this? And so here's a group that was practically forced into experiencing that reality of what's truly essential, because it had to fit on a USB drive, because that was the only way that they could share it. And so what would that mean for us when we can push more than that USB drive around in a minute through the network capacity that we have, where my hard drive is hundreds of times the size that it is? There's just such a contrast there. So thinking about DH on a stick, what is the most essential things about what we do, and how could we transport and share that? And are we making the most of the essential pieces, as opposed to just reaching out and grabbing stuff that's non-essential and ultimately not so good for the world in terms of its consequences?
So we just have another minute or two. So why don't we wrap up on one last question about what do you see as next on the horizon for minimal computing, whether in computer-based research practices or more generally?
Some of the most exciting work that I have done this year is in thinking about how we live, on the planetary level, we inhabit many different types of ecologies. So John outlined the contrast between Cuba and his environment in Canada, but I can imagine that even within Canada, you have Cubas. And then you have many other different types of ecologies. And one of the most exciting thing for me about my own thinking in minimal computing and folks here in our team is how do we think about a different range of how these possible technologies, maximal and minimal, can engage with each other, considering all these different ecologies. One example of that is some of the thinking we've been doing around how to respond in times of urgency, in times of disasters, when it's super predictable that hurricanes will grow in intensity in the region of the world that I grew up in, and that the damage is going to increase year by year, the human damage. And in what ways can we start thinking about how these sort of mixed ecologies can work to sort of mitigate some of that damage that is going to happen. John?
And I think we're pretty much out of time. There is a question here from Howard Nye, who's actually here on campus. So Howard, I apologize, we're out of time, but I'll follow up with you as an aside. Yeah. So I'm happy to finish with what Alex has said. So I'll underscore that. So thank you.
Thank you both.
Thank you, Roopika, for being a great chair. Bye, Geoffrey.
Thank you. Good to see you both.
Bye, John.
Thank you all for a great panel. Thank you, Roopika, for chairing this, and Alex and John for joining us. This is one of these sad moments when the conference comes to an end, but I'd like to acknowledge your contribution, and Roopika. So this brings our sixth Around the World conference to an end. Some of you may be joining Josh Kornblatt, and I certainly am, for a workshop in a few moments. Alas, that has a sort of limited number, and I think all the places have been taken in that. One of the things we do at the end is we acknowledge the people who have made this possible and the people behind the scenes. And I'd like to name a few people. First of all, Chelsea Mia, who's a PhD student here, who is also one of the leaders on campus in digital humanities, who has been the project manager and has really been the person who brought this all together, who connected us and so on. Oliver Rossier, who is the senior officer of the Arts Collaborative Enterprise, who has been a real believer and supporter of this, and is actually writing about it himself. I really owe him we all owe him a debt of gratitude for thinking of people and contacting them and believing in this. Adam Dombavari, who is the program coordinator for the Cool Institute, of course, is really the backbone of the Institute and makes sure that things run smoothly. Our AV technicians, Claire Peters and Grant Wang, who have come on this voyage all these years, and each year the equipment seems to get fancier and more interesting and smaller, which is actually great. In fact, this year, because of their expertise and their capability of moving around, we're doing it right in Hub Mall, which, for those of you who aren't at the University of Alberta, is a sort of central location. And so it's just fabulous to have people who understand it and give us options and work with us on this. There are a number of organizations, starting with the Office of Sustainability, who have collaborated with us. And I'll remind people that the Office of Sustainability has put together a great toolkit, which is available in PDF. If you just Google UAlberta Office of Sustainability, and they worked with us, or we helped them a little bit, but they were really the leads on this toolkit. eHub, which is the location we're in, the Entrepreneurs Center. I really want to thank them for hosting us and letting us take over their space and run wires all over. You can't see the floor, but there's wires with them all over the place. The Faculty of Arts has been a great supporter. And finally, of course, all the participants who took time to prepare talks, to have conversations in the background, and to make sure that this went well and were willing to share their expertise with us. So on this note, some of you have probably been dying to know how much, what the savings were of this conference itself. So I'm going to put up a couple slides that Chelsea and Oliver and others have put together. This particular version of the Around the World conference had participants from 20 different institutions, 18 cities, and 4 countries. And we figure that something like 48 metric tons of CO2 were saved by not flying all the people here. And something in the neighborhood of $36,000 was also saved. I want to add something that I don't think people fully appreciate about one of the values of this e-conference, that we were able to bring people into this conference who probably would not have come even if we'd had the money or been willing to fly, simply because they would have been too busy, or they don't fly, or this isn't their community, and they stay focused in other areas. So it's extraordinary that people, the willingness of people to participate when you offer them a lower impact way of participating and sharing their knowledge with us. And again, I want to thank all the participants. One last slide. The Around the World Conference is something that Oliver, Rossi, and I started working on. As I said, this is the 6th iteration of it. Over these 6 years, we calculate that we've saved something like 400 metric tons of emissions and $230,000. We've brought in people from 60 institutions, 18 countries. It's been a real pleasure to work with a breadth of people. We've had a number of institutes or groups that have returned and joined us year in and year out, depending on what the topic is. And I hope that we'll find ways to continue this and continue to work with our colleagues around the world. So on that note, I want to thank you all, and goodbye for this year.